Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 43 on probability densities.
We've seen that fair or uniform probabilities lead to geometry, to counting, length, area, and volume. But what happens when probability is not fair? In this lesson, we'll define and describe probability density functions.
In our last lesson, we computed probabilities under the assumption of fairness, namely that any point is as likely as any other point to be chosen at random. This is not always a good assumption. There are many instances where there's a bias, where certain outcomes are more likely than others. This bias is encoded in the notion of a probability density function, sometimes called a PDF. This is a function over a domain that tells you what outcomes are more likely than others, such as exam scores or heights. We define a probability density function, rho, as a function that satisfies the following two criteria. First, rho is non-negative, and second, the integral of rho is equal to 1. We have to specify a little bit more, namely a domain D on which we are discussing the PDF. So, in particular, the integral of rho over D equals 1. Now that's the definition, but it's certainly not a very intuitive definition. What does it mean? Before answering that, let's consider a specific example in the context of a collection of light bulbs. These light bulbs will eventually fail, but the question is, when? It happens with some sort of randomness, but how is this randomness regulated? Well, there's some underlying probability density function. Let's assume that it were exponential. That is, the light bulb is more likely to fail early and less likely to fail later on. This would be a function rho of t of the form e to the minus alpha t, let's say, where t is time and alpha is some positive constant. Is this a PDF? Well, it is certainly satisfying the first criterion. It is non-negative. As for the second criterion, let's specify a domain D for the time as 0 to infinity. Then, in this case, what would the integral over this domain be? Well, integrating an exponential function is easy enough. This gives e to the minus alpha t times negative 1 over alpha. Evaluating from t to infinity, we get 1 over alpha. This is not going to work unless, of course, alpha is equal to 1. So, what we could do is modify the PDF by adding a coefficient of alpha out in front. If we do that, then the integral is going to be equal to 1. Now, that's a good example of a PDF, but we still don't know quite what it means. Well, let's consider that meaning in the context of fairness, which we already have some experience with. Fairness connotes a uniform density function. That means a PDF that is constant on the domain. What would that constant be? Well, it has to satisfy the integral over d equals rho, that is this constant, times the volume of the domain. Now, in order to be a PDF, this has to satisfy that integral equals 1. So what does that tell us about rho? Rho, this constant, must be 1 over the volume of the domain. Let's see what that looks like in the context of the domain being an interval, let's say from A to B. B. In this case, rho is 1 over the length of this interval. That is 1 over B minus A. What would it look like in the case of a discrete or zero-dimensional domain? Well, let's say we had a die, a single die. Then the domain consists of 6 points, the different outcomes for the faces. The PDF would be 1 over the volume of this domain, volume in dimension 0 being simply counting. This means that rho is equal to the constant 1/6. If we had a different discrete set, let's say for flipping a coin, then since we only have 2 points in that domain, heads and tails, then rho would be equal to 1 over 2, or 1/2. Now consider this more carefully, because what we have in general is that for a discrete set of n points, rho, a uniform density, is the constant 1 over n. In the case of, say, flipping a coin, notice that the value of rho is precisely the probability of getting that outcome. You have a 50-50 chance for getting heads. If you roll a 6-sided die, your probability of landing on any one outcome is 1/6. Notice also what happens if you want to consider the probability of landing in a collection of outcomes. Let's say, what's the probability of getting 4 or 5? Well, we would add up these values of rho. 1/6 plus 1/6 is 1/3. Now, does that intuition carry over into the continuous case? No. The probability of landing at any single point in an interval is not 1 over the length of that interval. Not at all. However, if we take a sub-interval, then we can make sense of the probability in terms of lengths. If we consider with what probability does a randomly chosen point in a domain D lie within a subset A of D, then we have answered this question in the case of a uniform probability density function. We know that the probability of landing in A is the volume fraction. That is, the volume of A divided by the volume of D. We could write that as the integral over the domain A of 1 over the volume of D. But that is precisely the integral of the uniform PDF rho, that constant 1 over volume of D, but integrated over A, not over all of D. This leads us to consider more generally the formula that the probability, capital P, of landing in A with a point chosen at random is the ratio of the integral of rho over A to the integral of rho over D. And this explains why we want the integral of the PDF rho over all of D to be equal to 1, so that we can simply write the probability of landing in A as the integral of the PDF over the subdomain A. This holds in the uniform case, but it also holds in general. If we have a non-constant PDF and we want to know what is the probability of lying or landing in a subset A, we integrate the probability element, that is, rho of x dx, over the domain A. Let us interpret these results in the simple case of a domain being the interval from A to B. Given our PDF rho, what is the probability that a randomly chosen point in that domain lies between A and B? Well, by our definition, This probability P is the integral of rho of x dx as x goes from a to b. Well, that integral is, by definition, 1. What does that mean? When you see a probability of 1, that means yes, it will happen. But let's keep going. What's the probability that a randomly chosen point is exactly A? Well, that probability is the integral of rho of x dx as x goes from A to A. From what we know about integrals, that is equal to 0. When you have a probability of 0, this means no, it's not going to happen. What's the probability that a randomly chosen point is closer to A than to B? Well, we would simply integrate rho of x dx from the left point A to the midpoint of the domain. For concreteness, consider the example of a company that advertises half of its customers are served within 5 minutes. What are your odds of having to wait for more than 10? Let's assume an exponential PDF. Rho of t is alpha e to the minus alpha t over the domain from 0 to infinity. Our first problem is we don't know alpha, but we do know the probability of your serving time being in the interval from 0 to 5. That is, by definition, the integral of alpha e to the minus alpha t dt as t goes from 0 to 5. And we're told that that probability is 1/2. Now, we can do that integral easily enough, evaluating at the limits, and then doing a little bit of algebra to solve for alpha. I'm going to leave it to you to follow the computations and see that alpha is 1/5 times log of 2. With that in hand, we can now address the question of the probability of having to wait for more than 10 minutes. Now, we would compute the probability of being in the interval from 10 to infinity. Thus, we would perform the same integral as before, but evaluated at limits. T goes from 10 to infinity. This yields e to the negative 10 alpha. If alpha is 1/5 log 2, what is negative 10 alpha? It's negative 2 times log of 2. That is log of 2 to the negative 2 power. When we exponentiate that, we get 1 over 2 squared, or 1/4. That means that you have a 25% chance of having to wait for more than 10 minutes. That doesn't sound so good. But what are the odds of having to wait for more than 30 minutes? Well, we would follow the same computation and need to compute negative 30 alpha. That is log of 2 to the negative 6th. Substituting that in would give us odds of about 1.5%. There's one type of PDF that is of crucial importance that you're going to see again and again. This is called a Gaussian, or sometimes a normal PDF. This is the function rho of x equals 1 over the square root of 2 pi times e to the minus x squared. You've probably seen this before. This is sometimes called a bell curve. It has a peak around x equals 0 and then drops off. Now, there are a few things to observe. First of all, in this case, your domain is the entire real line. That is, this is a setting of infinite extent. Anything could happen. Your PDF is certainly positive. In fact, it's strictly positive. But the tricky thing is in verifying that it's a PDF. That is, in verifying that the integral over the entire real line is equal to 1. You're going to have to trust me on that for now. You don't quite have enough at your disposal to prove this. Now, you will often see Gaussians that are translated about some middle point or mean, you'll often see them stretched out or rescaled somehow. What I want you to know about Gaussians for the moment is that they are everywhere and all about. Gaussians come up in somewhat surprising places if you look at the binomial coefficients that you obtain from Pascal's triangle and consider what the rows look like. You notice that the rows tend to go up in the middle and then down at the sides in a manner reminiscent of a shifted Gaussian. In fact, if you were to divide these binomial coefficients by 2 to the n, where n is the row number, then you would obtain something that in the limit, as you go down, converges to something very much like a Gaussian. This is a hint at one of the deeper truths of mathematics, that Gaussians are limits of individual decisions, left or right, heads or tails, that compound upon one another to converge to such distributions. Gaussians are indeed everywhere.
So now we see not only what a probability density is, but also how to compute a probability by means of integration. In our next lesson, we'll introduce a few of the main characters of probability theory and see what role they have to play in our story of calculus.